Hi, my name is Tae Seng with the metric number SIF170056, currently taking final year project with the title Quantum Work in Evanescently Coupled Photonic Waveguide. So what is quantum work? The simple definition is the quantum analogy of classical random work. What is classical random work? Well, to understand classical random work, let's take a walk outside. This is Sam. Let's see what he is doing. He looks lost. Oh, he begins to walk around randomly each time he meets a junction, trying his best to find his home. We don't know where he will end up at, but we do know the probability he will end up at each vertices, and this process is called classical random work. Let's simplify this into 1D view. The walker is on the line at the origin positions having 50-50 chance of going right or left respectively, which is determined by tossing a fair coin. Quantum work is like classical random work, but the quantum walker can have superpositions of states. The probability distributions of quantum work tends to spread outwards, forming two main lobes at both extremes of the axis. We are interested in quantum work because it has a significant role in studying the evolutions of single and multi-particles. Besides, quantum work is anticipated as the solution for faster search algorithms. There are many platforms for quantum work implementations, such as nuclear magnetic resonance, superconducting circuits, as well as integrated photonics, which is our focus of study. We choose integrated photonics because it has long coherence time and low disturbance from the environment. The objectives of these final year projects are to investigate quantum work in photonics waveguide, to model and simulate quantum work in 21 arrays of waveguide, to analyze the ballistic and recurrent properties of quantum work. Two sets of 21 arrays of waveguide were designed by using RSoft AutoCAD, as I am showing right now. Here is a summary of simulation parameters. The difference in refractive indices for the two sets are shown here. Then, the simulation was done by using RSoft BeamProp. Let's see how the light propagates in waveguide for the case of set A with waveguide spacing 1.5 micron. Light is input at central waveguide, it begins to couple to the adjacent waveguide, then spread out in V shape. Eventually, it reaches the outermost waveguide, then it couples back inwardly. A plot of light intensity distributions at Z equals to 6400 micron gives the two oppositely main lobes. Beyond 6400 micron, we lost the quantum work properties. Here are the XZ contours of light intensities and the light intensity distributions for set A. The ballistic lobes are observed for the case of 1.5 micron and 2 micron waveguide spacing, while for the 2.5 micron and 3 micron, the light propagates with each waveguide for a longer distance. Thus, light intensity distribution does not have the ballistic lobes, but it is still spreading. For set B, the light intensity distribution looks almost the same, but quantum work occurs until 7200 micron for the case of 1.5 micron waveguide spacing. The log-log plot of the variance against propagation length for set A is shown. As we can see, the slopes are very close to 2, indicating the ballistic propagation of light. However, a slow time behavior begins to develop as the waveguide spacing increases. This is because for a larger waveguide spacing, the time required for the light to couple to adjacent waveguides are longer. The results are similar in the set B with slope of 2 and slow time behavior at larger waveguide spacing. For recurrent properties, the plot of light intensity along central waveguide x equals to 0 micron for set A is shown here. Notice that light intensity decreases along propagation distance. The humps in the plot shows that the light returns to its original site. For larger gap 2.5 and 3 micron, recurrent properties are not noticeable. as the light has not coupled to more adjacent waveguide. This is similar for set B. Calculation of Poisson numbers show it increased to 1 after only a few steps in Z. This indicates the recurrent properties of the quantum worker. However, this does not hold true for the case of 2.5 and 3 micron, as we can see from the plot of light intensity along central waveguide. The result shows that continuous time quantum work in n arrays of waveguide provide us a toolbox for controlling the quantum dynamics in a physical system. The simulation has shown that faster light spreading in smaller waveguide and light propagates within waveguide longer as the refractive index increases. The scalability of n arrays of waveguide also allows the possibilities of harnessing continuous time quantum work on larger networks. For future study, multi-photon quantum work and quantum work in disorder lattice can be investigated. In conclusion, we show that continuous time quantum work in evanescently coupled photonic waveguide produce ballistic lobes in the probability distributions. Besides, the ballistic properties and recurrent properties of quantum work are verified from the result. With this, I end this video and thank you for watching.